about other students? Okay, let me share my screen. Screen is visible? Okay. Please check your connection. Please mute yourself. Okay, everyone, my screen is visible. Those who joined, please reply so that I can start the class. My screen is visible. What about others? Okay, okay. So I'll start the class, okay? Rest of them will join. Okay. So today we'll study. Last class we have studied deflection of beam, right? And we have discussed two methods. Today I'll share the notes as a section. I have completed the same class for the section B also, so I'll share the notes today. Now today we'll go to structural stability, and in that we'll study about the stability of column. Okay. So first we'll see what is column. So a column is a structural engineering. A column in structural engineering is a vertical structure element that transmits through compression the weight of the structure above to other structural elements. So what happens if you see in a building, the loads, all the live loads and dead loads come to. Okay, first hope the live load and dead load is clear to you. Okay, any furniture you can take, those will be dead load, and we people will be called as live load, right? So our slab used to take our loads, right? And from that the load is distributed to the columns, and those columns transferred the whole load to the foundation. Okay, that's why we construct foundation, right? Foundation we construct the foundation part then we join the columns to the structure. So what happens, it transfers load to the in the vertical direction to the ground. Okay, that is the purpose of column. For the purpose of wind or earthquake engineering, columns may be designed to resist lateral load. So when you design a windmill or some structural frame, so for the purpose of wind or earthquake engineering, columns, they are designed for a lateral forces. There are different forces in when you design when you do a project on building design, then you'll understand about various designs of building. Due to lateral load, we consider some lateral load, wind load. There's a combination of loads, dead load, live loads, then dead load, live loads plus wind load. Okay, because wind will give up some pressure to the building, right? So in some structure we consider lateral loads also. Columns are frequently used to support beams or arches on which the upper part of the wall or ceiling rests. Same ceiling here it is representing by slab. So it supports beams also. Then a column is relatively long, slender member loaded in compression. So a beam always in compression plus tension, but your column is always in compression. Okay, it always compressed. When a perfect column is subject to a compressive axial load, the only deformation that takes place is the shortening of the column. When you apply a axial load to the column, what happens? Your column shorten. Okay. For low values of F, that is the load, if the column were to be deflected laterally by a force perpendicular to the column and the lateral force were thereafter removed, the column would return to its straight position, even with the force remaining in place. This indicates a condition of stability. So read this line carefully. Please mute yourself, those who have on, otherwise my voice will be echoed. Okay, okay. So for low values of f, that is the for low value of your load, if the column were to be deflected laterally, suppose this is your column. Let me note. Suppose this is your column. If you provide a lateral load to the columns, okay, if the column were to be deflected laterally by a force perpendicular to the column, so this is the column, I'm applying a load, this is called lateral load. The load which is getting applied perpendicular to the column, this is called lateral load. So if we applied that, then and the lateral force were thereafter removed, the column would return. So when I apply load, it will try to bend like this way, it will slightly bend. When I and the lateral forces were thereafter removed, the column would return to its straight position. When I remove the load, it will come back to its original position. So that is the stability. This phenomena is also known as buckling. Your column shouldn't buckle. If it don't buckle up, then your column is said to be structurally stable. Okay. If the load were increased, if the load F were increased, there is a value of F for which when the lateral load is removed, the column would remain in the deformation rate. Okay. So this line says that there will be a value of F, or you can say that there will be some kind of load at which your column will buckle, it will deform, it will remain in deformed shape. Okay. Let me try to draw in a blank space. Let me draw here. Okay. Suppose this is your original column. Hope I'm annotating and you're able to see. Is that okay? Please type in the chat box. I've drawn a column, circular column. Okay. This is, let me change my color. Whatever I'm annotating, are you able to see? This is the deformed
Yes,
shape.
ma'am.
Okay. This is the deformed shape of the column. Okay. This is the deformed shape of the column. So there will be some value of f at which your column will remain in deformed shape. Okay. This condition is referred to as buckling. So this situation is known as buckling, and the column is said to have failed from a structural standpoint of view. So generally what needs to happen, that when we apply this kind of load, your column should become straight. Okay. But when you apply a load, that at the load at which it will remain it's in deformed position, that then your column has failed, and this situation is called as buckling of the column. Okay. Now it says buckling can also be described in simple term as bending. Okay, you can say same. We have studied the deflection part. What happens? Beam was your beam was your horizontal member. Okay, it used to deflect like this, but column is your straight member, vertical member, and now it is getting deflected in this way, right? So this is nothing but you can also describe as bending, also bending of the column, and they have given a name of bending as buckling. Okay. Or bowing of a column due to compressive load. So it if a person bow like that, that is also like buckling. So they have said bowing of a column. Okay. When you do a namaskar in some part of the region, you go right, so like that. So hope this points are clear. Okay. When your what is the basic stability criteria, that it shouldn't be in deformed shape, it should come back to its original position when you remove the load. And what is lateral load? The load applied perpendicular to the column. And there one more word is described here, buckling. Now there is one more important, this is the important definition, slenderness ratio. So what is slenderness ratio? It is a measure of how long the column is compared to its cross-sectional effective width. Okay. So slender ratio is, this is the effective length divided by radius of gyration. We'll discuss what is radius of gyration. But slenderness ratio in simple terms is that how long is the column compared to its cross-sectional effective width. So let me note. This is, suppose I'm showing the circular column. Okay, you can take the example of rectangular, square column, anything. So slenderness ratio, it is the ratio of how long is this and what will be the width of this column. Okay, it is a ratio of how long the column, length of the column divided by its effective width. So this is the length, effective length. There is also one more term, effective length. For different loading, different support conditions, there will be different effective length. So slenderness ratio is the ratio of effective length of the column divided by radius of gyration. And what is radius of gyration? It has a formula of root over I by A. Okay, A is the area, I is your moment of inertia. Recall from your engineering mechanics, moment of inertia. Okay, Slenderness ratio has a formula of L by R. L is your effective length, R is radius of gyration. And again radius of gyration has a formula of root over I divided by area. I is your moment of inertia, A is your normal area. Now what are the failure modes of a column? Okay, now before that I want to discuss one more point. There some column are called as long columns, some column are called as short column. Okay, so there is a criteria also, we'll see later on. Failure mode of column. So number one is the failure mode of column is the buckling. When a slender member is, column is also called as slender member. Okay, column is also referred to as a slender member. Suppose if we have been given find the buckling of a slender member, or somewhere this slender member is used, it is also referred to as a column. So when a slender member is subjected to an axial compressive load, it may fail by a condition called buckling. So if I've been given, now it is talking about the axial load. Okay, so this is my column. This is my column. I am applying an axial load, and it can also buckle like in. Okay, it can due to the pressure, due to the compressive load, it will compressed, right? It will compressed, and it will deform like this. So this is the condition. This is also a condition of buckling. Buckling is not a failure of the material itself, but is due to the geometric instability of the system. So why this buckling happens? It doesn't happen just because of the material. Okay, it does. Sometimes it doesn't happen because just because of the material, but due to the instability of the system. Instability means the load we are applying may be not able. Maybe this column is not able to carry this amount of load. Okay, maybe we have designed the cross section of, we have designed a very long column which is not required in that area. Okay, so buckling is not failure just because of the material. What we are using the material here, this is not just only because of the material. It is also because of the instability of the system. Now how this instability comes? Maybe your column is too long. Okay, if somewhere if you need just 6 meter height column, and you are giving that 8 meter height column, so it is first uneconomical. First is uneconomical. Second, that it may not able to take that, the foundation below may not able to carry that amount, that height of column also. So that is one kind of instability, and the load we are applying is not suitable to take that. The load is very high comparison to the load a column can carry. Okay, so it is not just because of the material. Note that buckling is not dependent on material strength. Great, great. That is the point, that buckling is not dependent on material strength. So these kind of the important small point where 1 marks question can be comes, that buckling of material is dependent on. Okay, is independent of, like this. So you have to tick, the right answer will be, it is not, it is not dependent, or you can write independent of material strength. Okay, so let's discuss what is effective length. How a column is supported govern its buckling strength. Okay, your column will be supported, right, at both the ends. This is the column. Let me draw this time square column. This is my column. This will be supported at the base also, at the top also, right? So buckling strength is also dependent upon the support condition. What is the support condition? Just like in horizontal beam, we got simply supported beam, right? One was pinch, one was roller, right? We got simply supported beam, then we got cantilever beam. support condition. In the same way, there will be some support conditions for column also, and this buckling strength is governed, how a column is supported govern its buckling strength also. The effective length is also represented by LE, accounts for differences in the end supports. Now this LE, the effective length of the column, is also dependent upon the end support. There will be different values for LE for different support conditions. So let's discuss. What is effective length? Effective length is the length of the column would be if it were to buckle as a pin column. The dimensionless coefficient K, effective length factor, is used to calculate LE. So now there is a formula to calculate the LE. So these are see the table, effective lengths for columns with various end conditions. So the effective length is equal to the distance between points in the column where movement equals to 0 between pins. This occurs when the curvature of the column changes. The fixed free column is minor through the fixed end to visualize L equals to 2E. So this is the pinned. That means both end are fixed. Okay. Fixed free. Then fixed. Okay, this is the pin supported. This is the pin supported. That means two supports are hinged. Okay. This is both end are fixed. Here one is fixed. This one is fixed. This one is pinned. Let me draw. This support is pinned. See, this is the support, this is the pin, this is the same support like simply supported beam, right? This is the pin supported. Yeah, or you can say both ends are hinged. In this case, you can say that both ends are hinged. Now here your LE will be equals to L. Okay. Now this is the case of both ends are fixed. See, this both ends are fixed. Here your L will be 0.5 of L. That means L by 2. Note once again. So these are the values. For this, effective length will be L. For this, effective length will be 0.5 of L, or you can say half of L. When you have one is fixed, one is pinned, then you have 0.7 of L, and this one is fixed free. One is fixed and another is free. So here it will be twice of L. They have represented here. Okay, let me draw somewhere. So the first condition will be hinged. Just give me a minute. I'll try to draw. Okay. Just assume this one as straight. Okay. No, this is not working. Now it is straight, I guess. Okay. So first condition is that this is hinged. This is at the two end hinged. You can replace this part. So first case is that your column is hinged at the two supported. Then your effective length will become the same. L is equals to L. Now another one is sorry. First case is that your beam is hinged at the two support. Okay. There you have L is equal to L. Next case, this one, if I take fixed free, that means one end is fixed, another one is completely free. So here you have LE equals to twice of L. Okay. Next case is this one, fixed. That means both end will be your fixed. Both end will be fixed. Here you have effective length is equal to 0.5 of L, or you can say L by 2. Now the last case is one end is fixed and another one is hinged. What will happen? It will be effective length will be equal to 0.7 of L. Okay. So these are the four cases of effective length. And this is the length Effective length is equal to the distance between points in the column where movement equals to 0. So from this to this, here movement will be equal to 0. From here to here, this will be, the length will be effective length. Okay. Relative buckling strength, this is not required. So just focus on this effective length. Now what is radius of gyration? Where we got radius of gyration? We got radius of gyration in the in your slenderness ratio, right? This one was this here. Slenderness ratio was the ratio of effective length divided by radius of gyration, and radius of gyration has a formula of root over I by A. Now we'll study what is radius of gyration. So your radius of gyration, if all of the cross section area A were masked a distance r away from the bending axis, the idealized lump area cross section would have the same moment of inertia as the actual cross section. That is, if I is equal to a r square and distance r is the radius of gyration. There are generally two bending axes to consider and thus two radius of gyration. So in the x-axis we have one more radius of gyration, and you can take in y direction, you can take, there will be another radius of gyration. So let me take an example of rectangle member of length b and d. What will be the moment of inertia for this beam? What will be the moment of inertia for this beam? Please write in the chat box. Yeah, what will be the I value for this rectangular beam? Moment of inertia. Recall from the moment of inertia from the chapter from your engineering mechanics. What will be the moment of inertia for this rectangular beam? First day itself, I have said that please go back to your engineering mechanics, clear all your concepts. This I will be required in your every sub. This I moment of inertia is a very important topic. Go through if you are not clear with this. Anyone? Anyone from the class can tell me what will be the moment of inertia for this rectangular beam with B is with equals to B and D that is equals to D. Am I audible? 26 participants. Am I audible? Hello? Okay, okay. So what will be the moment of inertia? Go through this, okay? What is moment of inertia? It will be BD cube by 12. So today do one thing, go through moment of inertia, center of gravity, okay? CG, what is center of gravity, how to find the center of gravity and moment of inertia. For rectangular beam, circle, triangle, okay? These are the plane figures. Then there will be some unsymmetrical figures also like this one. Suppose this will be the member. Go through. That's why I've started from here, because in next classes there will be a called term shear center. So if you're not clear with MI and CG, how will I teach you the shear center? So please go through the MI and CG for plane figures. See, now this is the plane figures you can find out. Now this is the unsymmetrical figure. In X direction, it will be symmetrical, but if you take the Y direction, it won't be a symmetrical path. Okay. So I cannot discuss each and every in the class, and this is from your engineering mechanics. So please go through MI and CG. It will require in your last classes. So leave it. Let me continue. So these are the radius of gyration. So for X direction, it will be IIX. That means IIX means moment of inertia along the X axis. IYY means moment of inertia in YY direction. Okay. And what is radius of gyration? If all the cross-sectional area were massed a distance r away from the bending. So in every structure there will be a bending axis. So the distance between that cross-sectional area where your CG is lying, the distance between them is called r. Okay. And it has a formula of I by A. I is your nothing but moment of inertia of that beam. This is along the x-axis, this is along the y-y. Okay. So magnitude of the load at which buckling would occur. Columns are long slender members subjected to an axial compressive force. Lateral deflection on a column is called buckling. The maximum axial load that a column can support when it is on the verge of buckling is called the critical load. So the load, right, we have discussed the load at which your uh, column starts to buckle up. Okay, that load is called critical load. I have discussed just now, right? That mm, this is your column. This is your column. Then I'm applying a load, in this direction or this direction. Suppose I'm applying a load. Let me remove this part. Only axial load I'm applying. So this, when I'm applying a load, then it getting deflected. It getting suppose deflected. Okay, so the load at which it will remain in deformed shape, this is the phenomena of buckling, but this load is called as critical load. Okay, the load at which your column starts to buckle up, that load is called as critical load. Okay, that load is called critical load. So FOS is a safety margin given in design so that the member will not fail when the load is increased beyond the elastic limit or when the size is reduced. So there is a term called factor of safety. It is required in every structural member. What we do, we design the structure based on this FOS value. We give us some. Suppose if this load is can take 150 kilonewton, so we design with factor of safety of 2 or 3. That means we design with some more value. Suppose I'm designing my column can take 150 kilonewton, and I'm designing it with factor of safety of 2. I'm designing it with 180. So this is the safety margin. Okay, FOS is safety margin given in design so that member will not fail when the load is increased beyond the elastic limit. So its elastic limit is 150. So if it gets little, suppose it can take 150 and I have designed for 180. Suppose it is getting 160. So it won't fail. So that is the ratio is called FOS. Okay. Normally the factor of safety varies between 1.4 to 3. Now this is the range for column. For column, you take factor of safety from between 1.4 to 3. Okay, for different structure, there will be different FOS values. So you will get factor of safety in your design part when you do the design in the next class. So this is very uh, important term, factor of safety. And for the column, it varies 1.4 to 3. This is also will become your 1 marks question or 2 marks question. What is the factor of safety? What is the range of factor of safety for column? It ranges from 1.4 to 3. Remember, okay. Now in MCQ questions, you may get what will be the formula of radius of gyration. Okay, like this. So remember this formula. Remember these values also. Very important. During the numericals, you'll require. They will give you the condition. They will say that your beam is hinged at 2 points, hinged at supports. So you have to use this condition. Then they may say that your beam is fixed at 1 point and hinged at one support. Then you have to use effective length equals to 0.7 into L. Okay. So please mug up these values for different loading conditions. Okay. So this is FOS is P ultimate. That means what is the ultimate load it can carry. So my ultimate load I have discussed, that my load can carry till 180, but the allowable is 150. but it can take up to ultimate 180. So 180 by 150 will be your FOS. So you have to keep the FOS between 1.4 to 3. Okay, understood or not? You have to take the load between one. The ratio should be ultimate by allowable. Allowable means you can allow that much load. But if certain it can, the allowable is 150, but you are getting column 155. So that is it can take. It can take because I have designed the structure based on this FOS. So I have designed it for 180. So it can take 155. So ultimate is 180, allowable is 150. The ratio should be between FOS. Okay. Now this is called Euler formula. There is a Euler formula is given. Both ends are pinned so that they can freely rotate and cannot resist a movement. The critical load required to buckle the pin column is thus. Oh, this is the formula given. Derivation is not required. So this is the formula to find out the load carried by a column. PCR is also called as critical load or the Euler buckling load. E is your Young's modulus of the material. I is the least second moment of a. Okay, let me unlock. Okay, so I is your moment of inertia of the beam. LE is your effective length. Okay, so this is the general formula for finding the loads in a column. I square EI by LE square. Now there are some assumptions and limitations of the Euler formula that this formula can only be applied it when the load is axially loaded, when the column is loaded in the axial direction, this in this perpendicular direction. Column is perfectly straight, isotropic and homogeneous material. Isotropic, I said, the material is made up of entirely of the same material. Homogeneous is the same cross sectional. Material behaves within elastic properties that if you remove the load, it will come back to its original position. And both end of the column supports are pinned. So both the columns should be supported. Long slender members subjected to an axial. So the summary of this today's class: long slender members subjected to an axial compressive force are called columns. So what is column? These are the long slender members subjected to an axial compressive force. Axial compressive force. If I this is the axial compression. Why? It is in compressive direction, right? It is in compressive direction and the axially it is applying. So these are called columns. Now lateral deflection is called buckling. So this lateral deflection of the column is called buckling. Maximum axial load a column can support when the verge of buckling is called critical load. So what is critical load? The maximum load the column can support before buckle. When it starts to buckle, the load we are giving, that is called critical load. So that much about today's class. We'll continue this class in the next week. Okay, stability of the column. Then we'll move to another different topics. First, we'll complete. There is some numericals based on this formula. You need to know these conditions. Then you have to use this formula. This formula to find the various critical loads for a column. That we'll see in the next class. Okay. So please write your roll numbers in the chat box. फिर anyone left to write their roll number? Anyone left? Please write your roll number in the chat box. Last, Deepak. Anyone left? So any confusions, please do ask me. You can type in the chat box also. Why so less participants? What about others? Okay, hope everyone wrote their roll number. Okay, so in next week we'll continue this stability of columns and we'll do numericals. Okay, till then please from today onwards go through the deflection part, shear force bending moment, and clear all your doubts. In the next week you can ask me the doubts also at the end of the class. Okay, we'll continue with stability of column, but I'll take the doubts from last two chapters, shear force and bending moment diagram, and